Hello. So, allow me to continue. What I have spoken in the earlier thing was again a little bit from Schoenhauser's book, a little more from Remsburg book on this electronic heat management. And I have already shown you some heat sinks which are taken from the lab, which incidentally are commercially used. Some may be old and may not be appropriate. So, let me get back to the book again. And why, you may be wondering why I am reading from the book. It is not about reading from the book, it is that you should see the original whatever which has been written down. You understand? And the moment it passes to 2 or 3, it will only be retrieved previously. And I said, kindly I acknowledge the good work done by the authors, and I expect that you buy the book or contribute, acknowledge, and also get one for your library or for yourself personally. It is worth it. Now, let me get on with the lecture. I am repeating what has been done earlier. So, you see here, I will just point out, because there is no mouse in this case, if the regions are at equal temperature, no heat transfer occurs. Fourier's law can be used to predict the rate of heat transfer. The law suggests that the rate of heat transfer proportional to the area of transfer times and temperature gradient. Seen this, no? This is what I was telling you. Area, one is area here and temperature gradient. This is where you need to reread what is already written there. Thermal conductivity is generally expressed in terms of watts per meter. Meter is the running length starting from the beginning to end. You understand, no? In the direction of, I will use the word heat flow, or in the direction of the energy transfer. So, again I am trying to get you back to the old physics experiment where you have a can and then you have 3 pins of different conductivity. They are coated with wax, and then there is a small slider. When you put a hot fluid, they start heating, and you see that slowly the sliders will come down. The one which has the highest conductivity, that is copper, they will go all the way down. In between usually iron is used, or iron means now you only get mild steel, and then occasionally the third will be some non-conducting material where it does not move at all, but it does move a little. So, coming back to the this thing here, we have the relation is local temperature. The actual rate of heat transfer depends on conductivity, which is a physical property of the heat transfer media. And this is the next thing. Heat transfer can occur in any material, solid, liquid or gas. Conduction cannot occur through a vacuum. Conduction is not usually the predominant mode of heat transfer through a gas or liquid. Seen here. Heated portion of the fluid expands and sets up density gradients. In my earlier lectures, I have told you, I have given you a practical example of when you see thermals rising above any hot surface. So, right from a distance you can make out that if it is an exhaust pipe, you can see that the view behind is slightly distorted because the air is hot gas. And if you practice yourself, you can easily make out where is the source and so on. So, and then extreme example is seeing a mirage, where in the desert sand there are tremendous amount of this heating, and a thirsty person sees what looks like water. And I said the other pictures which you see in the cartoons are only a little bit of imagination. What he sees is what looks like water. Convective heat transfer, a microscopic method of energy, is much more effective than conductive heat transfer. The values used for thermal conductivity liquid and solids are generally obtained by experimentation. The thermal conductivity of gases at moderate temperature closely follows the kinetic theory, therefore calculated values may be used. As in this here, most important here, this is what I wanted to tell you, it is about, the issue is about experimentation. Without experimentation or trying to establish the actual what do you call conductivity coefficients in actual use, trying to extrapolate may not be that effective or useful, because even surface characteristics and the way of things are mounted and the way things are oriented, all of them seem to make a tremendous amount of impact. Now coming back to my this thing, Fourier's law presents heat transfer as a proportionality equation. Steady state proportionality, thermal conductivity can be found as K is identical to all these things here. The property of thermal conductivity is important in conduction and convection. In some natural convection applications where we have a confined airspace, heat transfer is actually by conduction, not convection as designer may assume. In some natural convection applications which have a confined airspace, that is, imagine you have an enclosure and we assume that there are thermals set up inside the enclosure, because we have mounted everything on a finned heat sink, then you have fins there, and we expect that the thing keeps circulating and so on, which may or may not be the cause. There is no place for circulation. Imagine both ends of the plate are blocked or things are otherwise confined. One of the things you will notice is that mostly maybe only conduction is available, everything else is not available. That is when people try to put a small circulator, a small fan inside the enclosure to ensure that you have convection. This is what now I would like to add, saying to the purposes of my lecturing about is, and why I need you to pay attention to what all I say. Whenever we have this problem, the designer may be thinking automatically natural convection takes place. It may not take place. That is where we probably need a small local circulator. Now these days fans which are only 30 mm in a square are available. Even if you tilt it and keep it and allow the local circulation, you can start convection again. And this we know about it. So thermal conduction can occur only when a temperature differential exists. Metals are good conductors, and so on and so on. The identical mode of energy transfer occurs during electrical conduction. This is why most materials that are good thermal conductors are also good electrical conductors. Primary exception to this is diamond. Diamond has a thermal conductivity value 5 times higher than copper, but a dielectric strength 10 times higher than rubber. Good, no? So we have this issue, diamond is still a diamond. Diamond has not been called a diamond just for fun. In the physical world, as I have written, there is a very good exception to the observation of the other materials like basic metals and non-metals, saying the identical mode of energy transfer occurs during electrical conduction as in thermal. So, some very rare cases, I do not know if it is still used, at least when this book is made, which is based on experiences in the 90s, and it has come out at about 2000. It was real. There were things also which are mounted on diamond. The thermal resistances characterize the transmission of heat in the path of heat transfer is expressed as rise in units as degrees centigrade and is found by this. This we have covered earlier. It sometimes become apparent which components are contributing to the heat rise of the air. Interestingly, they describe conductive heat transfer as a thermal resistance by this. You have seen this, no? We have this thing. Here also we have something by, that is degrees centigrade per watt, here also degrees centigrade per watt, and then you have here L by Ka, and then here you have the area which is used for affecting convection. That is where I showed you the heat sink yesterday. You have fins, and on the fins there are grooves, tiny grooves, they increase this surface area. So, surface is valid. Similar way, by rearranging various parameters and simplifying them, we also have, in the case of radiation, again same degree centigrade per watt, we have all this saying, the amount of material which is which is exposed, which I have shown you in the case of a practical heat sink. When we have deep fins, there is a shadow effect. Each fin will be forming a shadow in it. So, only the things which are at the bottom of the heat sink will be seeing the outside world. So, there are certain practical examples. So, we have something about the geometric factor of shape and so on. Now, in simple shapes such as a wall or a cylinder, the heat flow is one dimensional, that is, we require only a single coordinate. Oh, I think I skipped this. So, let me just show you degree centigrade per watt in the case of watt plus degree centigrade, diamond stays there, copper, beryllium, silicon, and the bottommost you have things like stainless steel, meaning for a given heat, the amount of for a given amount of wattage, amount of temperature rise is ridiculously high here. So, let me go further. Now, we come to these interesting things saying there are succeeding chapters give you things related to this analytical part of it, saying we have a area, then we have how heat is conducted from here, from there how this thing is taken out, and I have shown you a practical example of a heat sink on which a TO 220 package is mounted, and the total, this is typically the total area that is covered. When internal heat generation is uniform, all this stuff is given here. Rearranging the rate of heat transfer, temperature rise, we have everything has been reduced to a very convenient L by K into A. Problems of this type may encompass one dimensional heat flow, though any number of series and parallel combinations of thermal resistance. Parallel heat flow is technically a two dimensional problem. We can reduce it to a single heat flow direction. If you go to this is what is often used in all the lectures in electronic cooling. I said there are other lectures. Everywhere you see here, very important thing we need to consider here is, you have seen a beauty, on one direction we have a cold fluid. meaning it could be air, and the other direction internal to the whatever structure we have, and this can represent the wall. Followed, no? One thing you notice is whenever there is conductivity, high amount of conductivity, we see that the temperature gradient is very, very high. But the moment you come to the convection, here also you have it, but then you will notice here, have you noticed the small, the boundary layer seems to contribute tremendously. See here, only all the effect takes place only in the small boundary layer area. Why this picture is shown here is you have several K's here, you see here 1K, 1K, 1K. If we can somehow estimate these things depending on the difference in materials, so one of them, whenever there is a large temperature differential here, it could mean it could be an insulating material of some sort. You understand, no? And if you reduce the length, obviously we can avoid this thing, and then this can start here. The moment you have more and more length, you will have so many of these difficulties, lot of what you call temperature rise and so on. The other material could be your actual conductive material. So, the temperature gradient in a highly conductive material will be small, in a insulating material it will be high. So, if you adjust these parameters, in the end all you need to do is somehow, you have seen here, it is explained here, the wall is composed of 3 sections. Section 2 having the lowest thermal conductivity, section 2 section 3 is higher conductivity. Again here, no, we probably have some material which is the wall itself, and then these are insulators and all. So, if you go on to the heat transfer of these problems called composite walls, you see here infinity and so on and all that, no, by sigma. It is nothing but 3 materials ABC in series and convective heat transfer along the face of the material A and C, except the thing, can whole thing nicely we can make it into the usual resistive equation. You remember that, how to calculate equivalent resistance R1 plus R2. So, you have somewhere R1 plus R2 divided by the other things. You can, I think, in subsequent lectures the whole thing is clarified. So, all the heat transfer coefficients can be added. The advantages of these a resistive circuit like this is all the resistance can be added easily, just as you would do. So, resistance 1, 2, 3, then you have a temperature difference, and in the end we have a beautiful thing. We have overall heat transfer coefficient, which given a amount of power and you have given an amount of area, we directly can compute the effective circuit. You have seen this, no? This is what a commercial heat sink manufacturer will be giving. This is what I have spoken to you also earlier. In my earlier lectures, I have told you somebody has done the work for you. More than, I will put it the other way, somebody has evaluated these things, have catalogued it in standard conditions. You understand? Now, your equipment may not have the identical standard conditions which they have examined these things. So, I have given you an extreme example of a fan or a blower. In the description, they say this can take static pressure, or it can take pressure of 1 inch and then flow of 20 CFM. Intuitively, we think the total is valid. It is a lot like a switch. When you have a current, we expect the voltage to be 0. Same thing happens in the case of a fan. Static pressure very rarely we encompass, and usually the rise after the flow starts, the turbulence and all is taken care of and the flow increases. After that it follows a nice path. After a little while, the moment you reach the open, it is free. You understand, no? The moment you have no resistance at all. So, subsequently when we come to the blowers, you can understand the characteristic. It only one combination of back pressure and flow, it is optimum. Right now we are talking about the total amount of flow that can be got from the system. In reality, we have one more unfortunate factor, that is the electrical efficiency of the whole device. So, this is where the complications come. So, it is not just as if, then I have shown you what is called a 160 HD heatsink, and then I told you in extreme examples they will put one fan here and another fan here, a 150 mm or 140 mm fan on both sides, so that heat is taken across. These are to be observed. Now let me get back. Overall heat transfer coefficient in the previous expression is, you have this which I have shown. Notwithstanding all this, it is very much possible for using, in the case of a radial tube, you see here, you have seen this, no? If you know the various types of the physical parameters, and you know the actually conductivity of the solid, it is very much possible for us to do the necessary the necessary mathematical expression and try to get into absolute value, rate of heat transfer in the radial direction of the tube, which is given here, and this is what you are likely to find in all the textbooks. You have seen here, very important thing is, as you go across the wall, the more and more surface area is exposed. So, if something is steep, that means less conduction is taking place. Something is a little leveled out, that means the conduction is getting better at every interface. No, you see this beautiful thing you have. Where do such things occur? Anywhere. You could be having a cylindrical capacitor, or you could be having a core, a magnetic or otherwise something which also tends to get hot. That is where these relationships help. And combination of one face being heated, and as it goes, how well the fins, especially circular fins, how well they radiate, they exchange heat to the ambient, can now be happily modeled. You have seen here. So, you have here beautiful integrated or summated values. You see, this summation will take us here. Unless you take a worked example and do it for yourself, it may not make sense. And for me, it makes sense only when I need to explain to you that it is very much possible to accurately determine these things. Only thing we do not know is often this K is not very well known, very well defined, because sometimes occasionally K is also dependent on temperature itself, and a lot of it about the fabrication process. In certain fabrication process, the materials are compacted. Typically, best example is forging. If something is forged, the conductivity will be high. And if something is what you call made by some other thing, normal, especially if it is gravity die cast or gravity mold, there are always microscopic voids inside, and that will not have the same K, though it is aluminum. The one what we have done in by gravity die casting and sand molds will be very poor compared to something which is pressure die cast. So, if you see all your motorbike what you call engines and all, invariably all the items are pressure die cast. So, the conductivity is very high. In contrast to your experimental things what you are like to do, in case if you have seen my earlier enclosure design lectures, you would have, I have shown you a video on a water cooled power electronics module which we are making. If I get a chance and if it is ready, I will show you a picture as you mill it, and if you come close to it, you can see that there are small voids. This is where this K invariably varies. So, experimentally you need to find out. This is a beauty. So, we have all this beautiful heat conduction through a hollow sphere having a uniform surface temperature and no internal heat generation. So, I do not know where we can think about except maybe some shield which is used on top of it. I will avoid use the word making a bomb where probably there is enough heat generation. So, even ideal conditions like this spherical, actually more than spherical, usually hemispherical, the condition can be easily be calculated, and these expressions are used directly in computer packages, where if you specify the various things, the problem is broken down into manageable things like this. You have seen this beautiful thing, temperature and so on and so on. We have nice expressions can be evaluated, and if you are a person who can write code or about to write code, better you read it. So, you can always be happy that all possible combinations you see here there are beautiful combinations of type A asymmetrical boundary conditions, means one side temperature is different from the other side. Symmetrical boundary conditions, meaning you have both sides what do you call, you have seen this H A H B heat transfer coefficients on side A and B, and in the case both have similar things, and you have a what you call temperature of the surface. So, typically a fin may be able to behave like this, and finally if something is closed on one surface, the other surface here you have this by convective heat transfer things can be open. This is typically the case with an enclosure which is trying to transfer heat across. So, you may be wondering how they are able to make, yes, even if you see your the power supply unit which comes with your laptop, the whole thing is some plastic enclosure. So, I am sure you will have some burnt out power supplies. Next time open the top cover and see, most of the surface inside is probably one more metallic thing, occasionally aluminum, and it close in contact with the outside cover. The moment you keep it close in contact, and then you also reduce the thickness of the plastic enclosure, you have beautiful conduction across both the surfaces and an amount of cooling is possible. The second part is where your creativity is required, like that after you understand the rate at which things cool and all that, it is very much possible for you